Welcome back to this part three of the chapter 7. We just covered the sampling distributions in a situation where the sampling distribution is normal. Um, so if you have a normal sampling distribution, then it's very obvious. We can apply the formula that we had before. Um, but sometimes the shape of the sampling, or rather the population that we are sampling from is not normal. So if you're sampling from a population which is normal, it is not automatic that the sampling distribution is actually going to be normal. So sometimes you may have, because the random sample you assume is going to inherit the properties of the population that you are sampling from. Uh, but it does turn out that when you have these non-normal population distributions, uh, as the sample as the sample becomes bigger, it actually begins to approximate the sampling distribution. That is, the sampling distribution begins to approximate a normal distribution. So the shape of the underlying distribution uh, does not really factor so much if you're dealing with if the sample size is bigger. So you can see here, for instance, you have a population which is this is a uniform distribution over here. So this is a uniform distribution. So when the sample size is small, when n is equal to 2, you have this sort of sampling distribution. But then the sampling distribution begins to smooth out as n becomes bigger. So for n is equal to 5, you can see that you already have a smooth normal distribution. Same applies to this distribution over here, this V-shaped population distribution. Again, you can see that as the sample becomes big, you end up with a very smooth, typical normal distribution. This takes longer. So this is an exponential population distribution over here. So this takes longer to smooth out into a normal distribution, but eventually, as for n is equal to 30, so you find it's very typical in statistics to actually use n is equal to 30 or around there, around 25 to 30, because the assumption is that you can apply, if you're computing, for instance, the confidence intervals, then you can apply then you can apply this formula that we had before that rely on the empirical rule. We shall look at the empirical rule again at some point, which you covered in chapter 2, which gives you the proportions of the values that fall within a particular number of standard deviations of the mean. So I've already computed this to see the effect of the sample size on the to see the effect of the sample size on our confidence in a value lying within a particular range, a particular number of standard deviations from the mean. So let's move on to the sampling distribution of P. P is the proportion. So before we were looking at the sampling distributions of the mean, which would allow us to compute our confidence about values, means that we obtain from samples. But then the other thing is what kind of confidence do we have about proportions that we calculate from samples? By proportions, I mean, for instance, I think in this case study that we had before, we had about 60% of the 60% of the managers have taken a particular course. They have completed the management training program. These are 60%. In the sample, it is actually 63%, so it's actually a good sample. But then we want to see how that value actually changes depending on the sample. And again, it actually does change. It does actually change according to our normal distribution rules. So the expected value for the proportion is very similar to expected value for the sampling distribution mean. Is very close to the P. So this P, rather not the mean, the sampling distribution's proportion is very close to the actual. It is actually the population proportion. By that I mean, if you have a population where 60% of the population is where 60% of the population actually carries a particular characteristic. For instance, we could think about human beings. If you say, for instance, if you have 50% of the human population is male, so if that is the case, then if you do an unbiased sample, you expect that within that sample, that 50% are going to be male. So that's what this means. Yeah. So this applies. This can be shown to be the case. Then the standard deviation, the formula for the standard deviation is as follows. For the proportions, again you have this finite population correction factor. So this finite population correction factor I've already seen before. So again, it's going to be just a simple case of applying the formula for the. It's going to be just a simple case of applying the formula to obtain the actual standard deviation, and the formula happens to be this root p into 1 minus p over n. So anyway, let's see how we proceed. So if I think the best thing to do over here is to do a small calculation. So in this situation, for instance, we want to see the problem that we had before, and we want to see so you want to see, because we know that the proportion was 60% of the people that had been studied had taken the management training program, and you want to see what is the probability that they are going to fall between within 0.05% of that any sample that is obtained will have a population proportion which is 0.05%, well, rather 0.05 or 5% of the actual population proportion. So again, it's not going to be very difficult. If it is 0.05%, then we know it's going to be, I'm going to use Excel now because I showed you how to use Excel. So if you want to, so this is basically, we want to get the norm dist. If you're calculating this from first principles, obviously we'd have to first get, maybe let me first do that. So if you're going to do this from first principles, it's going to simply be, so you have to first get the z scores. So the z scores, it means you're going to get the, and then you're going to insert an equation over here. So for these different values, we want to get x minus mu over the standard deviation over the standard deviation. So we have to compute the standard deviation using this formula over here. So we already know the sample standard deviation. So the sample standard deviation was so the sorry, we need to get the population standard deviation, which is root. So first of all, let's get our standard deviation. St dev. So this is going to be square. This is going to give us. This is going to be the square root over, and the proportion is sorry, I mean the p is 0.6, I believe. 0.6 into 1 minus p, so that is 0.4. And all of this is actually over. All of this is over n. So n in our case is going to be 30. I believe n is still 30. If n is still 30, so let's see what do we get. And n is 30. Is everything closed properly? Point, and this is going to be times, and this is going to be, so we get the square root of that. So that gives us our standard deviation. So we have a point, so you want to have the value between, just a minute, the value is 0.55 and 0.65. Yeah, so these are the values that we want to deal with. So x minus mu, so we have 0.55, then we have 0.65. So x minus mu, so it's going to be computing the z scores. That is so that is the it should give us x minus mu must give us minus 0.5 divided by this value over here. So that is going to be and then here is going to be minus 0.05, and it gives us that value over here. Then of course this is going to give us the is it really giving us that value that we want? Okay, so this should give us really the positive value, 0.55902. So we want to get so let me just go back and teach you, because the goal is actually to show you how to use the so the goal is actually to teach you how to use the tables. So 0.55 is going to be, because we 0.559, so let's see the closest value to that. So 0.559 maybe is going to be 0.56. It's maybe we should round that off to 0.56. So let's see, 0.56 is over here. So you have a 0.7454. 0.7454 minus we're gonna have 0.56 is over here, 0.2877. So that's 0.2877. So you get 0.4577. So let's just see if this is what you actually have in the text. Population proportion. So let's see where that is actually taking us. So if we do have this, then so we have p is equal to 0.6. So the sampling distributions. So look at the sampling distribution. We've got the standard deviation. So this looks very similar to what we had, 0.0894. 0.0894, yeah. So that's what we have over there as the standard deviation. So when we calculate the so the other thing I forgot to talk about is that remember you're using the sample size of 30, yeah. So if you use the sample size of 30, then we do not need this population correction factor. So you don't need the final population correction factor, because n minus n over n minus 1 actually tends to 1. So we use this formula just like we did before. So anyway, so the computation that we were doing before, so here they're giving us 0.42. What did we get? We got 0.4577, so that's a bit off. Let me just be sure. What did we do here? 0.55, 60.894. So 0.5. Okay, we did. It's the rounding off, because they only do 0.55. So this is a bit high. Or should I say this is a bit low, because we actually do a 0.559. I do a 0.56 from the so the difference here is coming from the way, because I had to round off because this table is over here actually to two decimal places. This table is over here to two decimal places. But if I do it exactly as they do it in the book, then it's going to be, because they're using the Excel function normdist. So if I do normdist, then so for normdist, I'm going to put in the x, which is 0.55, the mean. So the mean of this is 0.6. The expected value, yeah, the expected value is 0.6. Then the standard dev is point 0.8944. Then the then is cumulative, right? Then I want to subtract pretty much the same thing. So I want to subtract this, but this time it's going to be minus, yeah. So that should give me, wait a minute, what did I just do? So it's 0.55. Okay, I'm thinking in terms of z score, so this should actually be, and that. So you see this value over here is actually 0.424, which is very similar to what we saw before in the book. Yeah, so this is pretty much all there is to proportions with our sampling distributions.